So now that we've talked about factory methods, let's turn our attention to the next and biggest piece of the pie for completable futures, which are completion stage methods. And you literally can see that this is the biggest piece of the pie. So there's the pie, and completion stage methods are the biggest piece, and that's how you can chain together dependent actions that are triggered when completable futures occur and complete asynchronously. There's a couple of different things that completion stage methods do. One thing they do is they can process the results of asynchronous operations when they complete, and they can also perform composition. So we'll talk about those two different things here briefly. Then we're going to go into more detail when we look at each of the different categories or subcategories of completion stage methods. So there's an interesting interface called completion stage, and this is what completable futures implement in order to be able to do this asynchronous chaining of dependent actions as operations that are running asynchronously complete. So a completion stage is something that can be done along the way to have a pipeline of result processing of dependent actions, which sounds like a big mouthful, but if you read the documentation and you watch my video here, again, you'll see how it all works. It's really, really cool. This is a very good web documentation page to read. So what does a completion stage do? It performs an action or computes a value when another previous completion stage completes. And that's why these are often called dependent actions. So the completion stages are dependent on the completion of one or more things that occurred before them. And we'll see there's a whole slew of these. There's actually quite a large number. I just have a few of them here that we're going to talk about. thenApply, thenAccept, thenCombine, thenCompose, and so on. I like to think about things metaphorically or through analogy. A reasonably good analogy here for completion stages is the idea of juggling. So if you're juggling, you know the goal is to try to hold on to whatever you're juggling, be it billiard balls or knives or flaming torches or running chainsaws, whatever people like to juggle. And while they're juggling, you keep it in your hand just long enough to either throw it back up in the air or switch hands and throw it back up in the air. So the idea is to have lots of things up in the air. And the things that are up in the air are analogous to the operations that are running asynchronously. And the completion notion here is like catching the ball and then getting ready to throw it back up again. So that's kind of the way to think about this. The other nice thing about this is that we only consume resources, at least processing resources. You consume some slight amount of memory resources all the time, but processing resources are only consumed when an action is actually running, which helps to reduce system overhead. Unlike synchronous operations where you actually block. There was a good question the other day on Piazza talking about whether the common fork join pool or a fork join pool is synchronous or asynchronous. And the answer is it depends on how you use it. And it really comes down to if you start an operation, a task that runs asynchronously, and you don't block synchronously waiting for the result, then of course it runs asynchronously. However, if you start an operation in the common fork join pool or any fork join pool, and you immediately block waiting for its results, then you're treating it more synchronously. Even though it will, in fact, run asynchronously, you're treating it from an application client point of view synchronously. So the answer is it depends. But in this case, we're going to let these things run in the background, and that will help to alleviate the overhead of a lot of blocking from the client point of view. So let's talk about chaining actions together. That's really the theme of completion stage methods. So we can chain things together using completion stage methods. The overall goal of this is to help make your programs more responsive by not blocking the caller, not blocking client code. People sometimes use client and caller somewhat synonymously here, but it's the thing that invokes the operation. And what happens here is that the dependent action will be automatically dispatched by the completable futures framework after a previous asynchronously executed call completes. And so here's a simple example, once again from the EX8 project in my Java 8 folder in my Live Lessons GitHub repository. And this particular example is going to start out by creating a big but unreduced fraction, a big fraction that's unreduced, and you can see it's pretty darn big. But by unreducing it, we say, don't bother reducing this, just create me a big fraction with this particular numerator and this particular denominator. The reason we're doing this is that reduction takes a while, and we want to run that in a background thread. The next thing we do is we're going to create ourselves a supplier lambda that will, in fact, reduce this unreduced big fraction. Now, remember, when we create the supplier lambda, it doesn't actually do anything. It just creates a reference to this lambda, to this supplier lambda. But no real computation has taken place yet. Computation will occur when we say supply async and pass in reduce. So we pass in the reduce supplier. At that point, that will arrange to have this run in the background. It will not do it right away. It'll arrange to do it asynchronously with respect to the caller. And as you may recall from our discussions of the internals of factor methods, supply async returns a completable future. And then in this simple example, we're going to chain the thenApply completion stage method such that this method will be called when the call here to supply async completes. When we finish reducing that big fraction that we passed in as a parameter, then this operation will be applied. And in this particular case, what it's going to do is it's going to convert that big fraction that's now reduced into a mixed fraction. So we take a so-called improper fraction, which always seemed like a funny name. We take an improper fraction and turn it into a mixed fraction. Only after this call finishes running asynchronously. So the question is, when supply async is called, what happens? And what happens is the underlying common fork join pool, in this case, arranges to run this reduction of this big fraction in some thread in the background. And the thread of control will just continue on. Now, if you look at the example here, you'll see that we have some clever ways of making sure we eventually get the results. But it will not block. And in fact, what's very likely to happen, in fact will happen in this case, is supply async will run in the background. This program will continue on doing whatever it does, ... When supply async is done, thenApply will be called in the context of that background thread that was running in the common fork join pool. So this reduction and, the reduction and the conversion to a mixed string will occur in some background thread. And if we want to get it back to some other thread, we have to do some other things to get the result back. And these examples show how to do that. Okay, so thenApply's action, that's what this thing is called here, big fraction to mixed string, is triggered when the completable future that supply async returned completes. And as we said before, this to mixed string call will be run in the background thread, most likely, almost certainly in the same thread that did the reduction here. The other thing you can do with completable futures, and as I've already said, but this is just taking it one step further, is you can chain them all together in a nice fluent way. So here you can see we're going to chain them using the Fluent Interface pattern. You've already been exposed to this many times now with Java sequential and parallel streams. And what's going to happen here is after this big fraction is reduced and converted to a mixed string, then the thenAccept call will be invoked. That's another completion stage method. And in this case, we're going to pass in a method reference to the system out println method, which will then, of course, print the result. That result will be printed in a background thread, not the calling thread, not the thread that invoked supply async initially. So here's the way to think about this. Each of these methods here, supply async, thenApply, thenAccept, register actions to apply when the time is right. Supply async registers this action to apply when the underlying worker thread in the common fork join pool is ready to do something. thenApply registers this big fraction to mixed string to be called back after we've finished reducing the big fraction, and thenAccept has an action that will print the results out. These actions, either lambda expressions or method references or whatever, these actions are only called after the previous stage completes successfully. And that, of course, raises the question, what happens if things go wrong? We will talk about that, though not today. And so when we talk about chaining things together using the Fluent Interface pattern, that's what we mean. That's what we mean. And you'll also notice something interesting here. These actions are deferred until the previous stage completes and the background fork join pool thread is ready to do something. And therefore, by chaining stuff together with the Fluent Interface pattern, it makes asynchronous programming look pretty much like synchronous programming. So this looks kind of like synchronous code in the sense that this happens after this, and this happens after that. But in fact, they're all running in the background. So that's kind of cool. It's kind of the best of both worlds in a way. All right, so that is the end of the discussion of completion stage methods, part 1. Next week, we'll talk about part 2.